All right, everyone. This lecture is about sets, and it's a first lecture for, I believe, is chapter 3 of the textbook. Okay. All right, we're going to review quickly some of the basic definitions of sets, and you should also try to read the textbook on chapter 3. All right, so we're going to go over set definition, notations to build set, Venn diagram, size of a set, inclusion-exclusion principle, Cartesian products, power sets, and then finally the partition of a set. So part 1 lecture is very much about definitions, and part 2 is about a bunch of practice problems. All right, so a set is a collection of distinct objects. So there are some basic examples of a set. For example, a set A contains 3 integers. This is a set, okay? It's very important to notice that it has to be distinct. So if I have A prime that I say is A1, 1, 2, 3, keep in mind this is not a set, okay? The first one is a set, the second one is not a set. Some basic operations, you will see this symbol a lot. This means belong to. So X is an element of a set A, or it means X is in A. This is again a predicate, and it can be evaluated at true or false. For example, is X a variable or does X refer to the letter? You have to be very careful throughout. If I say X is an integer, a natural number, that means X belongs to the set of natural numbers. Or if X is an element in the set that contains element X. Okay? And sometimes you have to also pay attention to the domain that is being used. In most problems you're going to see, we're going to specify the domain. For example, some of the common domains or common sets, you have seen this before. Z is a set of all integers. N is a set of natural number. And when we use n here, we assume that it starts with 0, okay? But sometimes in different textbook, it might start with 1. So we have to be careful. Q is a rational number, and R is the set of real numbers. And sometimes there is some common ones. For example, this is positive integer, this is negative integer, this is or positive integer and including 0, which means non-negative integer. This is positive reals. Those are some of those common ones, but in general, don't make up your own, because if you don't define it, people wouldn't know what that notation means. Okay? So in most cases, at least in this lecture, our convention is capital A and capital letters were used to denote sets. And we typically use lower letters for variables or element in the set, for example, lowercase x. And in this case, our case matters. If you write all caps, please try to practice using letter cases that is appropriate to get ready for quiz number 3. So for the quiz and homeworks, we reserve uppercase for sets, lowercase for set element or variables. So there's some more set definitions. One is subset equal. What does this mean? This means for any element X in set A, it's in B, or other words, A is a subset of B. If you see this symbol, it means it's a proper subset, meaning that A is not equal to B. Okay, so what does this mean? If I'm thinking about a picture, if A is a subset of B, this is a set B, A is inside, that means it's smaller, and which means specifically there at least exists one element that is in B, but not in A. Okay, so B is strictly larger than A. And of course, A equal to B is to say for any element in A, if and only if it's in B. Essentially, those two things are equal. This is a very nice property. What does that mean? Is that if I say A equal to B, this is logically equivalent to the statement that A is a subset of B and B is a subset of A. And later on, when we do proofs on set, you might end up using this property. Okay, so this is a nice property to remember. Of course, we have more set definitions. An empty set is a set that contains no element. The common symbol for empty set is either this or this. Okay. And finally, we have U, which corresponds to the universal set. And usually in the context, it's a set that contains all possible elements. And in the context, every set is a subset of the universal set. So another way to think about it is it's the biggest set in the context. And you will see this universal set in the context of the Venn diagram. Okay. So let's go over our first set proof. This is not a problem for you to solve by yourself. This is just, we're going to go over this proof together, okay? So what do we want to prove is empty set is a subset of any set, okay? So the way we're going to do this is to prove by contradiction. When we prove by contradiction, the idea is to assume there's a counterexample and then prove that the counterexample leads to a contradiction, which means there is no counterexample, which means the original statement is true, okay? So what we do here is we suppose there's a counterexample. A counterexample to this statement means for any set A, there exists an element in the empty set, and this element is not in A. What does this mean, right? This means I have an empty set, but empty set is not a subset of any set. So I assume A is any set A, and we want to say that this is not a subset. That is a counterexample, okay? So if I want to show empty set is not a subset of set A, then that means there's something in the empty set that is not in A, okay? So that's why X is that something. So that's my element. So whenever I want to show one set is not a set of another, it means there's some element in the first set that is not in the second set. So this element is X, okay? So we assume that there exists an element in the empty set such that it's not in A. But because empty set is empty, by definition, that means X actually does not exist. This is a contradiction. So in a sense that this proof is only one line, is to say that, well, if empty set is not a subset of a set A, then there must be an element in the empty set that is not in A. But because empty set is by definition empty, so X does not really exist, that's a contradiction, okay? So you're going to see many more proofs involving sets later. And then for those problems, you need to combine what you learned from chapter 2 with what you learned in chapter 3. Okay. So when we actually want to build a set, we usually have a format which is starting from the name of the set, and then the domain, and then the predicate. For example, if I want to define a set of even integer, I want to say, well, first of all, well, actually in this case, it's a set of positive or non-negative integers that's even, okay? So that's one way to define it. The first thing we specify x equal to x in n is the domain, and then predicate is to say x is even. So what is the property associated with the element? Of course, based on what we learned for the chapter 2, you can also see that the set can be also defined that, you know, it's, first of all, it's non-negative integer. and it's equal to 2k for some, again, non-negative integer, okay? So again, what does this set mean? This is a set of all even natural numbers, okay? But let's do another one. What about I want to define the set of all even integers, okay? So I just need to, so what is the set of even integers? Again, by definition, what I'm going to do is I'm going to use the symbol A. In my element, my domain is x is, of course, it's integer, such that x is equal to 2k for some k that's integer, okay? So again, the first part here, x belongs to z, that's my domain. So where my even integer come from is coming from the set of integers, that's a domain. But the predicate is I have to evaluate it true for the predicate to be a member of my set. So in this case, I want to define the set of even integer. That means my element in the set has to satisfy the predicate that is equal to 2 times some integer. All right, next one. We have the notation of set intersection, set union, and set difference, okay? And of course, there's also the universal set. So when we say set intersection, A intersect B, it means it's a set of elements that is in all possible, the set of all possible elements, such that it belongs to both of them. If I take the union, it means the element in there belongs to at least one of them. And if I take the difference, it means it belongs to A but not in B. So of course, something you're going to see later is essentially the Venn diagram. So if I have two sets, A and B, if I visualize them, the shaded region is the intersection. Now, same thing, A and B. If I take the union, everything in A and everything in B is in union of A intersect B. If I take everything in A but not in B, it's this shaded region. All right. So two sets are disjoint if they have zero intersection. So again, in the Venn diagram, you can have set A like this, set B like this. There's no intersection. Now, if I take the complement of A, so if this is my universal set, meaning that it's all possible set element, actually should be capital letter, let's be careful. And now if this is my set A, then the outside, I'm going to use a different color. Everything in green is what's called a complement, which is everything outside the set, everything in the all possible elements, but not in A. And everything in the universal set, but not in set A, okay? Now, there's a set of properties, and this is going to look very familiar to you because this almost looks like logic operations you learned in chapter 1. But in here you have, in terms of set operations, you have a bunch of properties, including commutative property, associative property, and distributive property. So if A intersect B is equal to B intersect A. So if I swap the order, the intersection produces the same results. Same thing with union. A union B is equal to B union A. Again, if I swap the order, the result doesn't change. Associativity is if all operations is intersection, for example, whether I take intersection of AB first and then intersect C, or if I intersect B and C first and then intersect A, the results are the same. Similar property applies to all union operations. Finally, distributive law looks very much like De Morgan in the logic operations. So this is very important here, is that if I take A intersect the union of, oh, sorry, it's not De Morgan. Let me take it back. It's actually just distributive law. If I take the intersection operate on each element, and then you union the final result. Similarly, if I take union with intersection, you just distribute the union operation across intersection, okay? So I made a mistake, ignore the De Morgan comments. All right, so finally we have Venn diagram, which is a way to kind of demonstrate the relation between sets, okay? Usually, when you actually drew this diagram, you remembered to always show the universe, which is basically universal set, which is the largest possible set in the current context. Always show the general case, meaning that, you know, any two sets that have some regions that overlap and some do not. This is a general case. So if I'm talking about A union B, I'm always sort of thinking about the following setting, where there's some intersection, there's some overlap, there's some don't overlap, okay? Unless there's a specific reasons not to, we are going to use this kind of formulations. And also you should not include descriptions like this. Okay. So now let's do a quick practice problem. We want to illustrate those are set equivalents. So what we're going to do is we're going to do the left-hand side by the Venn diagram, and then we're going to do the right-hand side and show those two diagrams looks the same. Okay, so let's again put the set into general position. First of all, if I want to do left-hand side of this, I'm going to have three sets, okay? And I'm also going to show the universal set. This is set A, this is set B, this is set C, and then the rest of it is a universal set. So first of all, I'm going to demonstrate what is B intersect C. This is the region that is shared by the set B and set C. A does not come into play yet. So I'm just going to color this area that is B intersect C. Now the next thing I'm going to do, since I'm still operating on the left-hand side, I want to look at A minus B intersect C. What does that mean? That means everything in A, but not in the intersection of B intersect C. So if I want to visualize everything A, but not in the intersection, so I want to look at what is in A and kind of looks at this piece that is in B and C. Okay, in A, but not in the intersection of B, C. So the picture I should really use color, so let me just use color. This is yellow part, okay? So this is a slightly better drawing example, identical to the previous slide. Now I'm going to do the right-hand side, okay? Right-hand side has several operations. One, I take the difference between A and B. Two, I take the difference between A and C. Then I'm going to take the union. So I'm going to do it step by step. First of all, I'm going to visualize A minus B. Then I'm going to visualize A minus C, and then I'm going to visualize their union. Again, I'm going to start with sort of general position of the three set. A. Oh, well, we drew it. A, B, C. A, B, C. A, B, C. Okay. So first of all, everything is in A. Let me just A, B, C, U, A, B, C, U. Everything in A, capital U. Everything in A, but not in B. That's that. Everything A, but not in C. Okay. and finally the union of those two, okay? It essentially looks like, again, it's equal to everything in A, but not in the intersection of B and C. So that's how we prove the equivalence is once I reach this part, so better drawing here, keep in mind the right-hand side looks at this piece right here, right? And that is equivalent to the left-hand side, okay? So that's how we sort of illustrate those two sets are equivalent using the Venn diagram, okay? So just to quick review, when we have the symbol n, it means the size of a set. So if I set n, set A, n of A is a size, so number of elements. Sometimes we also use a symbol like this, okay? So let's do this quickly. If I give you 3 sets, tell me the size of this set, okay? This is where you can pause it for 2 minutes and look at the size of each set, the size of their union for a pairwise union, and the size of their 3-way union, okay? So this is when you pause the video, okay? But I'm just going to go ahead and solve this. If you want to count number of elements, the sets are very fairly small right now, so I can count it directly. So if I do some counting, the size of A, there's 8 element, so that's 8. Size of B, there is but there's actually there's how many are B? There are 7 plus 2, there's 9. How many elements are in C? There is 10 plus another 10, there's 11. All right. Okay. So now what's interesting is looking at what's when I take set union. Of course, if A and B are disjoint, right? Naturally, if I union them, their size should be their sum together. And we'll see this formula very soon. But what you need to do is to identify what is really happening between A, B. That's how many elements are being shared between them, okay? So let's look at A union B directly. So let's look at everything in A already. So I have 2, 6, 7, 9, 10, 11, 12, 13, 16. That's already in A. And when I take the union, I should make sure my element is unique, right? Distinct. So if I just first put all the elements in there from B, I need to remove some of them because they're not unique. So I need to remove, if they duplicate, I need to remove the duplicates. So what do I do? Let's say I will use this color. 2 showed up already in A, so I remove the 2 as a duplicate. I remove 9 as one of the duplicate. 11, 12, 13, that's duplicate. So how many do I have remain? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That is the size of A union B, okay? You're going to do the same thing with A union B union C, again, removing duplicates. And I want you to solve this on your own. And of course, next slides, we're going to give that solution. Okay. So there are some very interesting formula involving sets operations. When I take the union, the number of elements in A union B is we take both sides of the set and then removing the ones that is being counted twice. So the formula is essentially the size of A union B is the size of A plus size of B minus the part that has been shared. If you want to have a mental picture, this is what you have as a mental picture. Imagine I have 2 sets, set A and set B. You know that the element that is in A but not in B is counted once. So everything in here is counted once. everything in here is counted once, but everything that is shared between the two sets is counted twice. So you need to kind of remove the duplicates in the intersection. That is a high level intuition about this formula. Of course, now you have 3 sets. I need to remove even more duplicates. Okay, if I have A union B union C, that's the size of A, size of B plus size of C, minus the duplicated ones between AB, between AC, and between BC. However, if I do this, I actually remove too many. I need to add them back. So what does this mean? If I have A, B, and C, okay, let me just make sure I also color it so it's not misleading. Everything counted once is the yellow region. And things counted twice in here are the blue region. So using the same philosophy, everything counted once are in yellow because those are unique to A, B, and C. So those are counted once. Of course, now I need to be a little careful to look at the area that is counted twice. So that's right here. Those blue region are the regions that is counted twice. And finally, the middle piece, which I'm not going to try to cover, that white area is what's being counted 3 times. Okay. So this is a good practice for you to think about how would you actually prove this equivalence. And later on, you're going to see a lot of proofs involving sets. Okay, so let's begin with example. And again, we're going to do this example together. Let's say my domain is all the positive integers or positive reals between 1 and 1,000. So another way to write this out, this is 1, 2, 3, up to 1,000. Okay, so this is my the domain. But we want to count the size of the set where it's all the elements between 1 to 1,000, such that either 2 divides y or 3 divides y. What does that mean? That means it's either divisible by 2 or divisible by 3. So in this set, if I'm thinking about it, what are some of the examples from this set? I would say, well, 2 is divisible by 2, so 2 is definitely in this set. Probably 4 is in this set, okay? And 6 is divisible by 3. Well, 3 is divisible by 3, so 3 should be in there. And 6 should be there because it's actually divisible by both 2 and 3, and so on and so forth, okay? But because we want to count what's in this set, what I can do is I can define, if I'm thinking about the inclusion-exclusion formula, I have what's in A and A or B is what's in A plus what's in number of elements in B minus their intersection, the size of intersection, okay? So I really need to figure out in this case, what is my A and what is my B? Of course, remember this is all condition. That means it's essentially the union of 2 sets. Okay, so what is the first set? The first set is basically my set A is a set. Set A is all the element between 1 and 1,000, such that it's divisible by 2. So 2 divides it. The other set B is all the element between 1 and 1,000, such that it's divisible by 3. And what is in both A and B? This is the element in my domain that is divisible by both 2 and 3, which means it's divisible by 6. Okay. All right. So if I want to, again, going back to this formula, to count this blue formula to count how many elements is in A union B, I need to figure out how many elements in A, how many elements in B. Okay. So the first question, how many elements in A? There is 1,000 possible numbers. How many of them are divisible by 2? So how many even numbers do I have? So basically, I have 1,000 divided by 2. I take the quotient, that's 500. Same thing for how many elements I have for set B. Again, take quotient. Finally, if I look at what's in A and B, I'm going to take quotient of divided by 6. And now I'm going to put all these numbers into the formula. I get this. Okay? So let's make it a little bit more complicated, right? This is an example where you have to use the three-way union formula. Okay, and then this is a good time to pause and to see if you can solve this problem on your own. And we already put a little bit hinting here, right? If this is if the set A is a one such that it's divisible by 2, set B is such that it's divisible by 3, set C is such that it's divisible by 5, then you have to look at the size of each of those sets. Okay, so essentially, if you think about this is a formula right here, you need to look at the size of each set, A, B, and C, and then their pairwise intersection and their three-way intersection. Okay, so in this case, what is a two-way intersection? Two-way intersection is divisible by 2 and divisible by 3, right? So it should be divisible by 6. Similarly, if it's divisible by 2 and divisible by 5, it has to be divisible by 10. If it's divisible by 3 or 5, it has to be divisible by 15. And finally, if it's divisible by 2, 3, and 5, it has to be divisible by what? By 30. Okay? So nothing surprising. Again, you count how many elements in each set, and you apply this formula. This is a very, very important problems. I would encourage you to try to solve it on your own first before you look at the solution. All right, one more concept. What is a Cartesian product? If I have two sets A and B, we can define A cross B to be a set of ordered pair. So what do I mean by set of ordered pair? It means it's taking an element from A, take an element from B, and you form each pair to be an element of this set. Okay, and sometimes we can use the notation A cross B. Okay, so for example, if N is my set of non-negative my set of real numbers, which is a non-negative numbers, then 1 and 1 is an element in the Cartesian product, 2 and 1 is an element, 3, 2 is an element. Similar in this picture, 4 and 6 is an element. So you choose an element from the first set and an element from the second set and form a pair. And that pair became an element in the Cartesian product of A and B. So I can generalize from 2 sets multiplying together to n set multiplied together. So you get what we call n tuples. So for example, I have set S1, S2, and I also have up to Sn. Each set, you can use x1 to represent an element in the first set, x2 to be an element from the second set, and so on. What we do is we basically pick an element from the first set, pick an element from the second set, and element from each of the following set, and that forms an n tuple that is part of the Cartesian product of those sets. If each set is the same set, sometimes we simplify it using the power form. Okay. So let's say I have 3 propositions. They can be evaluated either true or false. then what we want to do is looking at what is sort of the Cartesian product of the set B against itself, multiplying 3 times. So what is B cross B cross B? So this is looking at all possible combinations of element. I choose an element from each set and combine them together to form a triple, okay, or 3 tuple. In this case, if I choose a true from the first set, the first B set, that is T, and I choose false from the second one, or choose false from the third one, that form an element in this product space, okay? So in this case, for every set, I have 2 choices. Combined, I have 8 possible combinations, okay? And you can validate this by hand. Okay, and also this is a number of rows you are going to have when you are actually writing a truth table involving 3 propositions, P, Q, and R. Okay, because those are the all possible combinations of their true and false value. So you can do this and you can keep growing, and you know that in this case there's going to be 8 rows. So there are 8 possible combinations of element choosing from each of the B set. Lastly, there's a definition of what's called set of sets. What is a set of sets? If you think about a set as a box of element, then set of sets is really a boxes within boxes. So it's element in a set of sets is a set itself. For example, on the right-hand side, this is a set. It contains only 2 elements, and each of the element is a set by itself, okay? So it's very important to notice that the set 1, 2 is not a subset, but is actually an element from the set, okay? So this is a bit different. So remember when you use a symbol, this, it means it's an element. If you use this symbol, it means a subset. So now let's say if this is my set A, what is an actual subset? A subset, remember, is formed by a subset of element in A. So for example, if I choose one single element in A, that as a set is a subset. So you need to form it like this. So why is this interesting? For example, in the classic definition of subset, if I have a set A that has 3 elements, then a subset B is a set that is taking a subset of element. So in this case, B is a subset of A, okay? And how to form a subset of A is take the element from A and form a set. So first of all, let's use the yellow part. The yellow thing here, what I'm drawing, is an element from the set A. But I'm taking it out to form a subset. I need to make it into a set. So I put an extra pair of parentheses, which is this right here. So now this is indeed a subset, okay? Another way to look at it is what is the size of the set of sets A? There's only 2 elements, so the size is actually 2, not 5, okay? So set of sets, if I go to the next level, it can accommodate a mixture of different type of elements. For example, in here, my set A contains 4 elements. The first 2 elements are just numbers. The third and the fourth element are sets themselves. Okay. Now, let's ask what element of A is also a subset of A. Okay. And then this is where you can pause the video and think about this for a minute. Which element of A is also a subset? Okay. It turns out this answer is element 1, 2, because 1, 2 is an element of A, which is highlighted in yellow. Okay. However, if I take element from A, I can start forming subset. if I take the orange element from A, which is the number 1 and 2, I can actually form a subset 1, 2, which turns out to be the subset of A, okay? So in this case, the statement, this is a subset and this is an element, is true, but keep in mind, those actually are talking about different things from the set. When I say it's an element, it's actually the yellow one. When I say it's a subset, it's actually formed by the orange ones, okay? All right, lastly, you're going to see a lot of appearances of the concept of a power set. So a power set is the set of all subsets and is best explained by example. So in this case, if I have a set that contains 4 elements, 1, 2, 3, 4, I'm going to list all possible subsets. And in this case, first of all, the most important part, which people often forget, is the empty set is always a subset of the set A, okay? So my question is, if my set A is an empty set, what is the power set of A? Okay. This is a take home. And you should try to convince yourself whatever solution you come up with and go to the office hour and ask this question. Okay. Now, let's look at the set what contain 4 elements, 1, 2, 3, 4. I'm going to list all possible set. I'm going to start with a subset that has 0 element, which is empty set. Then I know the subset 1, 2, 3, 4 each contains a single element. Then I'm going to look at the subset that contain 2 elements, 3 elements, and 4 elements. If I do this carefully, I will see that there is a total of 16 elements. Okay. But what if my set now became larger and I want to ask the size of the power set? It became a little bit tricky because you need to start thinking about how to best enumerate all possible subsets. But it turns out there's another combinatorial way of thinking about this. Okay. And the combinatorial way of thinking about it is actually, if you think about there's 5 elements, each time I form a subset, I have 2 choices. Either choose this element or not choosing this element. So for each of those elements, 1, 2, 3, 4, 5, I have 2 choices. Okay, I can choose, either I choose 1 or not choose 1, choose 2, not choose 2, choose 3, 4, 5. And later on in the semester, we're going to study combinatorics. And this is a simple problem of combinatorics. In order to form a subset, I need to make a choice on each of the elements, either to choose it or not to choose it. So I have 2 choices. And because I need to form the subset, I need to perform all 5 steps. So for each step, I have 2 choices. Total, I have all those 2 choices multiplied together. That is equal to 32. Okay. So there is actually a proposition that you can prove if I give a finite set A, if it contains k element, then the size of the power set is 2 to the power of k. The one I gave you earlier, this formula here, is from the argument of combinatorics. But we can also prove this statement using induction. Okay, so now you can pause this video and try to prove this by induction. Okay, so let's do a sketch of the induction. The most important part of induction proof is to figure out 4 steps: problem statement, base case, induction hypothesis, induction step. However, usually we use n as a variable for induction, but here n is reserved for counting the number of elements in a set. So instead, we need to think about a different variable. So if you look at this, it says for a set of any size k, the power set has a size 2 to the power of k. So it looks like actually the variable I want to use is k, because as I increase my set size, I want to prove it inductively, okay? So the problem statement, let's say I'm going to say P of k is a statement. The P of k, the statement is for a set of size k. If a set A has a size k, then the power set is of size 2 to the power of k. So if I'm using implications, I want this, okay? But now let's look at the base case, right? Where I have finite set, we can either start with case, let's start with case 1, when k is equal to 1, okay? So basically in the base case, we want to show the statement P of 1 is true. What does that mean? That means I want to show if I have a set of size 1, its power set satisfies this formula, okay? So before I do that, I'm going to introduce a few more variables to help with my argument. I'm going to use A of k minus 1 to represent a set of k minus 1 elements, okay? And then A of k to be built upon the previous set of k minus 1 element, except I'm going to add an extra element, and I call that extra element E of k. Okay, so the base case is to show P of 1 is true. That means for a set A of size 1, its power set is of size 2 to the power of k, which is 2 to the power of 1. So what does that mean? I want to show that is for a set of A1, then I want to show power set of a set of size 1 is 2 to the power of 1, which is 2. This is true because if I have a set A1 that has only one single element, then its power set is in fact the empty set and the set itself, right? Sorry, not using the set element. Let's use the elements in there. It's denoted by E1 as the only single element. So let's be careful here. Let's say A1 has one single element represented by E1. Okay? Now for induction hypothesis is we want to assume P of k minus 1 is true. Of course, you can assume P of k is true and prove P of k plus 1 is true. But in here, let me assume P of k minus 1 is true, meaning that the proposition involving the variable k minus 1 is true, which meaning that the number of elements for a set that has k minus 1 element is equal to 2 to the power of k minus 1. This is part of the hypothesis. Okay. Now we want to show the statement P of k is true. You know that the set with one more element from the set AK minus 1 is just adding an extra element. We just need to figure out what is the extra subset that happens when I increase my set size. Okay. So first of all, we want to say A of a set AK of size k in this definition here is built upon the previous set by adding an extra element. Okay, that's our first thing. And now, by using this property and the property that A of k minus 1 is a subset of AK, we know that the power set of AK minus 1 is a subset of a power set of AK. Because all possible subset of a smaller set should be elements in P of AK. So what do I have? That means if I take the difference between these two, so I want to look at everything that is in the power set of AK, but not in the power set of AK minus 1, should be the element or the subset that is formed by involving this new element EK, right? So what did this mean? This is equal to or element S that is big S that is part of the set that is one element smaller. You take that element and you union E of K. So what did this mean? That means I am always forming a subset and from a subset from the previous set. So let me give you an example. If I have my set A is 1, 2, 3, and or actually let's just say 1, 2. My set, this is set of size 2. Set of size 3 is built from the set 1, 2, and I add an extra element 3. Then the power set, the difference between these two, is always formed by the element 3 with subsets of A2. So what did that mean? That means I'm going to form 3 with empty set, which is, so let's say power set of A2 is what? Is empty set, set with one element, and set with two elements. So in this case, I'm going to use 3 and form a new set with an empty set. Take 3, form a new set with a one element set. Okay. And take 3 and form a new set with a two element set. Okay, so that's the difference. So this is exactly the same philosophy here in the general proof. So when we have this, let's say when I have this, you know that, well, on the right-hand side, any new element, new subset I'm forming has to involve this extra new element EK. So the size of this is actually equal to the size of the power set P of AK minus 1. So what we have is this is equal to 2 times power set of AK minus 1. And I'm using induction hypothesis. This is equal to 2K. Okay. Of course, what I just went through is a sketch of the proof. Here is the detailed proof. Okay. Finally, we're going to go through the definition of the partition of a set. So if you have a set A, I'm going to divide it into sets of sets. A partition means that for any element that is in my partition, they are non-empty. So for example, I have element A, a set A that has, let's say, 3 elements. I'm going to partition it into 2 sets. For example, I'm going to divide it evenly. So a partition would be having a set of sets. This is an example, right? I'm dividing it into a set of 2 sets. And then this form a partition when it satisfies the following 3 conditions. 1 is each set is non-empty. 2 is for any pair of set, they are disjoint. And 3 is their union form the original set. Okay, that's the definition of a partition. So there is example problems here to show that A have this form. So this is a place where you want to pause it and see if you can solve this problem. We might have to revisit this question again because this is a very important problem to help you understand the concept of a partition. But let's start looking at the definitions. A is actually a set of all even numbers. B is a set of all odd numbers. And we want to show that A and B together form a partition of the set of integers, okay? So in order to check it's a partition, it has to satisfy 3 properties as before. Remember the first property, each set has to be non-empty. Second property, their pairwise intersection is empty, meaning that there's no overlap between the sets. And then 3 is that the union of those sets form the original set. So intuitively, what does this mean? Let's say I have, let's start from -3, -2, -1, 0, 1, 2, 3. This is my set. This is my set of integers. What it's saying is that if I take out or the even number and then take out, and then the remaining is going to be the odd number, and even number and odd number form a partition. So we need to first check that each of those set of even number or set of odd number, each of those 2 sets is non-empty. Well, this is very easy because we know that clearly for 0, for example, is an even number. So the set of even number is non-empty. 1 is an odd number. So the set of odd number is non-empty. Okay. Now we need to show that they're disjoint, meaning that a number cannot both be even or odd, right? Meaning that they have no intersection. The way you prove it is to prove by contradiction. Assuming there's an element that is both in A and in B, that means this element here can be expressed as both as an even number and an odd number, okay? So, well, there's a definition of even and odd, and X is both even and odd. This is a contradiction, but another way to prove a contradiction is to say if X is equal to 2K, meaning that it's even and it's also odd on the right-hand side, what you can do a subtraction of things on the left. You get something on the left, which is 2 times some number, which is, again, the even number. And on the right-hand side, 1 is an odd number. Again, you get to the contradiction that an even number is equal, 1 is an odd number, but 1 is an even number, but 1 is actually odd. That's a contradiction, right? So let me rephrase it. If I express 1 as 2 times k minus p, by closure property, k minus p is an integer. So 1 is expressed as 2 times some integer, which shows that 1 is even, but 1 is actually odd by definition. So that's a contradiction. Okay. So the next part, which is showing that the union of those 2 sets form the entire set. Again, you can prove by contradiction. You can prove by cases, okay? Let's consider an element that is integer. We want to show that when it's even number, it's part of A. When it's odd number, it's part of B, which means there's no element that is in the set of integer Z that is not in A and it's not in B, meaning that every single element is covered by either A or B, okay? So that is a proof. Again, we might have to visit this again in the recitation and so on, okay? So now if I have set, let's see, I have 2 more slides. Now there is a property we have seen before. If I have a set A with k element, then the size of the power set is 2 to the power of k. Okay. Again, if I have a set S, which is a special set, it just contains 2 elements. They're called binary numbers, either 0 or 1. Then, of course, using the same definition, what is the number of power set of S. This is 2 to the power of 2, which is 4, right? But then if you take a bunch of binary, a set containing just binary numbers, you take their Cartesian product, it turns out the number of elements in their Cartesian product is going to 2 to the power of k. Okay. So in this case, for example, again, if k and this thing here equal to this here. So there is a mapping essentially between the size of my set S to the power of k and all the possible subsets of A. Okay. So there is a one-to-one correspondence between these two sets. Okay. So what you do is for any subset in the power set can be represented as a k tuple from the set Sk. And the k tuple is formed by whether you choose an element or not. So let's look at the situation. If my set has 3 elements, I'm going to look at the power set. And a particular subset, for example, empty set, means that if 0 means I choose element 1, 0 means I don't choose it, 1 means I choose it, then empty set means I don't choose any of those elements. So that's 0, 0, 0. Again, let me list the 3 elements. I can either choose it, which is 1, or not choose it. So if I choose both 1 and 3, then I list a 1 here, but I don't choose 2. I put a 0 here. This form a tuple, and this tuple is an element in S to the power of 3. Okay, similarly, if I'm looking at a subset 1, 2, and 3, which is a subset of a power set A, then it's corresponding to choose all 3 elements. Okay. All right, one last slide on the definitions. If I have 2 sets A and B, and then A is a size K and B is a size M, now the question is, what is the size of their Cartesian product? So it turns out if I have 2 set A, their size of Cartesian product is their size multiply each other. So in this case, I have K times M. Now the interesting part, what is the power set of the Cartesian product? That is, of course, 2 to the size of the set. And of course, the question is that which one is larger? Usually, this term is larger. Okay. Now, let's go even further. What is the Cartesian product of the power set of A and B? Okay, so you know the size of the power set of A is 2K. The size of power set of B is 2M. So the size of their Cartesian product of those 2 power set is going to be 2K times 2M, which is 2 to the power of K plus M. So the question is this first term usually bigger than the second term? The answer is not always. Is because when K is equal to 1, M equal to 2, then the first term is 2 to the power of K. The second term, 2 to the power of 2, the second term is 2 to the power of 3. So in this case, K plus M is actually bigger than K times M. When K is equal to 1, M equal to 2, right? 3 is bigger than 2. Okay, so not all the time. All right, that's the end of the part 1 of the set. If you have any questions in the lecture, please feel free to come to the office hour or ask during recitation.